In section 7.4, we're going to learn how to integrate pretty much anything that has a sum or difference of squares in it. And we're going to be doing that by introducing some trigonometry into the integral, which usually to most of my students sounds absolutely crazy that you would voluntarily put trigonometry into a problem, but it's actually going to make our integrands simplify very nicely if our integrand contains a sum or difference of squares. And the reason for that is because of the Pythagorean identities. All of our Pythagorean identities can be written as sums or differences of squares. So we've got sine squared theta plus cosine squared theta equals 1. I'm not using x here because our integration problem is most likely already going to have an x, and we don't want to confuse the two variables. And then we've got two others. We've got tan squared theta plus 1 equals secant squared theta, and 1 plus cotan squared theta equals cosecant squared theta. And we could manipulate these equations, move terms from the left to the right or whatever we need to do in order to get them to match a sum or difference of squares, depending on what we need. And then we are going to do a transformation of our integral so that the sum or difference of squares in our integral simplifies really nicely with the Pythagorean identity. So the first part of this video is we are going to talk about how to decide what substitution you're supposed to do. There is a rule on how to do this. We're not only going to be using the Pythagorean identities from trigonometry, but the Pythagorean theorem from algebra and geometry class. It's got the exact same pattern, except it uses algebra instead of trig functions. So the Pythagorean theorem says if we have a right triangle, you can square the legs of the triangle and add them together, and that will give you the square of the hypotenuse. So it's a squared plus b squared equals c squared. And actually, we don't have the squares on the triangle. So if we've got a triangle with side lengths a, b, and c, and a and b are the legs, then the Pythagorean theorem says if it's a right triangle, those legs will always have the relationship that a squared plus b squared equals c squared. Well, this formula also has a sum of squares, or if we were to move one of the terms from the left to the right, we could make it a difference of squares. So it is very similar to our Pythagorean identities. That's why they share that name. The only difference is our Pythagorean identities contain trigonometric functions. So our goal is to get these expressions in our integral, these sums or differences of squares, to match up nicely with a Pythagorean identity. And there is a trick to get that to work out nicely every single time. Anytime you see a sum of squares, like in this case, you know that you're working with the two legs of the triangle. If I were to pull one of these terms from the left over to the right, we could also write this as a squared equals c squared minus b squared. So anytime you see a difference of squares, like this, we want to remember that the first term is always the hypotenuse. And the second term is always going to be a leg. And which leg you assign it to is completely up to you. The A and the B there are interchangeable. So what we want to do when we see a problem, and I'm not going to frame this as an integration question quite yet, but if we want to use trigonometry to simplify the expression 2x cubed over the square root of 9 minus x squared, we're going to use a trig substitution to simplify it. When I first look at a problem like this, especially for an integration problem, I would know that I need to try trig substitution if I see a sum or difference of squares in my integrand. And because we have a difference of squares here, I know from what we just said that that first piece has got to be c squared and the second piece has to be b squared. And I'm going to draw a triangle that matches that. If c squared is 9, that means c is going to be 3. And then if b squared is x squared, that means b is x. And then you can do the Pythagorean identity, the Pythagorean theorem to figure out what an expression for the missing side is. We know that a squared plus b squared equals c squared. We have replaced b with x, and we have replaced c with 3. So if I want to come up with an expression for my second leg there, I'm going to have to solve this equation for a. So first you'll subtract your x squared over, and then you will square root both sides of the equation, and it gives us an expression that we can put in the spot of our second leg. Now oftentimes it's going to match what you have in the original expression with a square root, but that's not always going to be true, so we can't depend on that. So if this is truly a right triangle, that other leg must be the square root of 9 minus x squared. Our textbook says that you can just memorize which substitutions you need to do. I am not a big fan of memorization. What I strongly suggest is every single time you see one of these problems with sums and differences of squares, you remember that if it's a sum, then they both have to be legs. If it's a difference, then the first one is the hypotenuse, the second one's a leg. So that's pretty easy to remember, especially if you're familiar with the Pythagorean theorem. And we wrote that up here just a minute ago. And then we use that information to set up a triangle to match the situation that we're working with. Now the key in figuring out the correct substitution to do, you always have to label an angle that you're going to be working with. So I've got my theta labeled there at the bottom left. We want to set up a trig function that does not use the difficult side. So you can look at this triangle and see that two sides are really easy and one side is difficult. Obviously this one with the square root is our difficult side. So I'm going to set up a trig function that does not use that side. It uses my other two sides. So if you remember from trigonometry, that is called our opposite side, and that one is our hypotenuse. So we want to set up the trig function that uses opposite and hypotenuse, which is sine. So sine of theta equals opposite over hypotenuse. And if you solve that for x, you will have the substitution that you need that will make that sum or difference of squares in your problem simplify very nicely. So in this case, if we let x equal 3 sine theta, we'll be able to get 2x cubed over the square root of 9 minus x squared to simplify very nicely. So I'm going to go ahead and plug that in, and we'll see what happens. So instead of 2x cubed over the square root of 9 minus x squared, everywhere I have an x, I'm going to replace it with 3 sine theta. So I've got 2 times 3 sine theta cubed over the square root of 9 minus 3 sine theta squared. Now be careful when you do this because we're almost always going to have a coefficient. And if there are any powers being applied to your x, they not only are going to be applied to your trig function, but also your coefficient. And that's a common mistake that I see in these problems. So now I'll apply those exponents. So 3 cubed is 27, and then sine cubed over the square root of 9 minus 3 squared is 9, and then we have sine squared. So I've got 54 sine cubed over the square root of 9 minus 9 squared. So right now this does not look any easier. In fact, you might think this looks more difficult. And that's because we're not done. We now can actually apply a Pythagorean identity to simplify this piece. You can always simplify. If you've done the right substitution, you will always be able to simplify your sum or difference of squares. So there under that square root, I am going to factor out the 9. They have got a 9 in common. And when you pull it out, you'll be left with 1 minus sine squared. And that is a Pythagorean identity. 1 minus sine squared is equivalent to cosine squared. Now you might be thinking a few steps earlier, well, everything is a perfect square. I can go ahead and just take the square root of each piece. And you actually can't because of the subtraction sign. So the goal of these last couple of steps is to get the expression, the sum or difference expression, actually written without any sums or differences, which we can do if there's trigonometry in there, because all of those sums and differences with our trig functions have a replacement that's just a single term. So now that I have no addition or subtraction in there, I can take the square root of each piece, and it's just 3 cosine theta. So my entire denominator just simplifies down to 3 cosine theta. (54) divided by 3 is going to be 18, I believe. And then sine cubed over cosine, it would probably be better for us to rewrite that a little bit. Just one of the sines over cosine is tangent, and then we still have 2 more sines in the top, so sine squared. So we're able to simplify 2x cubed over the square root of 9 minus x squared all the way down to this trig expression. And that's going to be our goal here with trig substitution, is to first and foremost figure out the correct substitution to do, and that's where I like to use the triangles. The triangles are very helpful because all we have to do is avoid the difficult side, and then remember how to set up our different trig functions with either opposite, adjacent, or hypotenuse, and then solve that equation for x, and it tells us exactly what substitution to make. Once we do that substitution, we're always going to be able to simplify the sum or difference of squares, because we created this entire substitution based on that sum or difference of squares. So it works out very nicely every single time. Now our ultimate goal is going to be to integrate this stuff, but let's look at one more, just simplifying problem. We want to use a trigonometric substitution to simplify this. This time we have got a sum of squares in the problem. And based on the Pythagorean theorem, if you've got a sum of squares, we can think of those as being the legs. So the very first thing I do is I'm going to set up a right triangle that mimics the pattern we see in our sum or difference of squares. I know that one of my legs is going to be x, and the other leg is going to be 1. And if we work with the Pythagorean theorem out, we can figure out what the hypotenuse is. It's going to be the square root of x squared plus 1. To figure out the substitution we want to do back in our expression, we are going to set up a trig function that avoids the difficult side. Avoid the difficult side. So I just want to use my opposite side and my adjacent side. So we need to think about what trig function uses opposite and adjacent, and that's tangent. So the tangent of theta is opposite over adjacent, and we really don't have to do anything with that 1 there. We get that x equals tan theta. That is the substitution we need to do in this particular expression to get our sum or differences of squares to simplify with the Pythagorean identity. So now I can go back in to my expression and replace all of the x's with tangent. So I get 5 tan theta times the square root of tan squared theta plus 1. Now you cannot cancel the squares and the square roots here because of the addition. But if we can figure out a way to rewrite that where it doesn't have addition or subtraction, then we will be able to square root it. And that's where our Pythagorean identity comes in. Tan squared theta plus 1 is a Pythagorean identity. Tan squared theta plus 1 is equal to secant squared theta. And now that I've eliminated the addition, I can just do the cancellation of the square and the square root. So this one simplifies down to 5 tan theta secant theta. I'm going to show you one more. Anytime we see a sum of squares, we're going to end up using tangent. And the trick to make sure it always comes out to be tangent is to have x on your opposite side. We want x on the opposite because when we set up this fraction, we do opposite in the numerator, adjacent in the denominator. If for some reason x ends up in the denominator, then in order to solve, we're going to have to use reciprocal functions. So we would have to change it into cotangent. But if you always put x on the opposite side for the sum of squares, then it will always end up being a tangent substitution. The same is true for this one up here. Anytime we have a difference of squares, and there is a number first and a variable second, you again want to have the variable, you want to have the x on the opposite side. So in both of these cases, when you set it up, you want your x to be opposite your theta. Now this third one I'm going to show you ends up a little bit different. We want to simplify 2x squared times the square root of x squared minus 16. So this one again is a difference of squares, but if you compare it to the first one we did, there is a significant difference in the two problems. In the first one that we did, we had a number first and a variable second, and that's going to make a difference when we set up our triangle and figure out which substitution to do. In the first two problems we did, we said the substitution works out best if the variable is opposite of your theta, but that's not going to be possible here because we also said when you have a difference of squares, the first piece is the hypotenuse, and the second piece is going to be a leg. So it's not going to be possible for us to put x opposite our theta. So when we set this triangle up, x has to be the hypotenuse. It really doesn't matter whether we put 4 on the opposite leg or the adjacent leg, but just to give you a little hint that will save us from having to backtrack and do some erasing or make this problem any harder than it possibly needs to be, it will probably work out nicer if you let this value be your adjacent side. And remember, I'm not pulling that exact value out, I'm pulling its square root out because we're matching this up with the Pythagorean identity. So we're matching this up to say c squared and b squared. And when we label our triangle, we only label it as c and b. So when I pull those numbers out of the sum or difference of squares, I'm always doing their square root. And then the opposite side here is going to end up as the square root of x squared minus 16. Once we get the triangle set up, we're going to do just like we did before. We want to avoid the ugly side. We want to use those nice simple sides. So this is the adjacent side, and this is the hypotenuse. So cosine uses adjacent and hypotenuse, but hypotenuse ends up in your denominator. In order to solve for x here, we're first going to have to get x out of the denominator, and that will give us x cosine theta equals 4. And then we're going to have to divide the cosine over in order to isolate our x. And I'm not going to leave it as 4 divided by cosine theta. There is a trig function, a different trig function we could write instead of having cosine in the bottom, and that is secant. So the substitution we're going to do for difference of squares when the variable is first is secant theta. So now we can use that information to rewrite our expression. We've got 2x squared times the square root of x squared minus 16. And we want to replace all the x's with 4 secant theta. And then I'll go ahead and apply my squares. And remember that doesn't only apply to the trig, but also the coefficient. So this is 2 times 16 secant squared theta times the square root of 16 secant squared theta minus 16. So in the front, we really have 32 secant squared theta. And then inside that square root, we will always be able to simplify that with a Pythagorean identity. So both of those terms have a 16 in common. And if we factor the 16 out, we're left with secant squared theta minus 1. We cannot just cancel squares and square roots when there's still addition and subtraction in the problem. So our whole goal here is to figure out which trig identity is in there and replace it with its single term equivalent. So secant squared theta minus 1 is equivalent to tangent squared. And now that we've eliminated the subtraction, and it's all just multiplication inside, now we can just take the square root of each piece. So the square root of 16 is 4, and the square root of tan squared is just tan. So I've got 128 secant squared theta, tan theta. So our goal is to get all of these sums and differences of squares to actually be written as trig expressions. And then we can refer back to all the different methods we used in 7.3 for integrating trig integrals once we finally start writing these problems as integration problems. So in the next video, we'll actually look at these as integration problems because there is one more thing that we have left out that we will see once they are written with integration.